All right. So this is the last two lessons are like the beginning of the next, like the rest of the semester here in this class. Calculus, really, a big thing about calculus is how quickly things are changing, okay? And slopes are super important in calculus because slopes tell you how things are changing. Slopes of secants tell you on average how quickly something is changing, okay? But if we're concerned about a location, say this location right here, and I want to figure out how quickly is my function changing. Well, think about these 2 points that create the secant line. And take those 2 points and bring them closer and closer and closer together. Every time you move them closer and closer together, you get a better and better approximation for what's going on right here. That makes sense? And then move them closer and closer together until they're practically on top of one another. Okay? And all of a sudden you connect that teeny tiny line, you extend it, and you create this line right here. It's a tangent line. And we're talking about putting them infinitely close together. Well, if you're infinitely close to something, you're pretty much on something. But it's just enough away so that you can't say it's like exactly on the same value. You can't have a line if you don't have 2 points. Well, our 2 points are from 2 points infinitely close together. Okay? And it's all about the slope of this line. The slope of this line is the instantaneous rate of change of the function. Okay? Now, slopes of tangents and instantaneous rate of change is pretty much all we're talking about for the rest of this semester. Okay? Now, I don't want to have to say instantaneous rate of change and slope of tangent every single time. It takes me too long to say it. Okay? It took mathematicians too long to say that. And probably when you guys are talking to your friends, your brothers and sisters, like, oh, have you gotten to derivatives yet? And you were like, no, I haven't gotten to derivatives yet. And then you probably asked them, what's a derivative anyways? And they were probably like, I don't know. Well, what is a derivative? It's just a quick and easy way to say slope of a tangent or instantaneous rate of change. Just a way for us to quickly say that. Okay? It's like a fancy math word. I'm going to even write that down. It's a fancy math word. So now when somebody asks you, what's the derivative anyway? You say, it's really just the slope of a tangent. And we know that a slope of a tangent takes, a secant line that gives us an average rate of change, and it makes it an instantaneous rate of change if you put those points together, infinitely close together. Okay, so now throughout the rest of this course, if I say one of 3 things, do you have a question? Okay. If I say one of 3 different things, it means the same. Okay? If I ask you, what is the derivative? That's the same as if I ask you, what is the slope of the tangent? Which is the exact same as if I ask you, what is the instantaneous rate of change of the function or of something at a specific value? Okay, they're all the same. 3 different ways to say the same thing. So when we talk about derivatives, you're thinking slopes of tangents. You're thinking change, okay? The rest of this course this semester is all about how things are changing. Well, we first introduced kind of tangents with motion, but let's just talk about just functions, How can we find an exact value of a slope of a tangent of this function? We got this 3x squared minus 2 graph, and I'm going to focus on this location x equals 2, okay? And I want to figure out how quickly is the function changing. We could see this function goes down and then up, okay? But how quickly is it going up at this moment? This is where, we think about, okay, if I find the slope of this line, I'll know how quickly it's going up. Now, slope. Okay, we know slope formulas. We know how to calculate slopes. If you had a calculator, and you're going to discuss this with your neighbors, what would you do to get a great approximation for this slope? And then what would you do to get an even better one, an even better one? Discuss. All right, so Miss Bowman, I know it's slope formula. What are you going to do with that? Miss Bowman, what are you going to do with that slope formula? What are you going to plug into it?
I was going to do one point, like, put the function in calculator and then find what 1.99 was and 2.001, and then use that as the value.
That's exactly right. This is great. It's just slope, right? And we talk about, well, if we put our points really, really close to 2, we'll get a better and better approximation of what's going on at 2. So let's do that. Let's plug in 2.001. Let's use 3 zeros. Let's go for it. And then 1.999. If you have a calculator, you can do that. I'm going to show it up on the board. And that's the change in my y's, and then the change in my x's. Three zeros. It's going to be this. All right. So let's make it look nice and pretty. So I'll do our fraction. I actually just learned this last period. I did not know that alpha y1 gave you the fractions. So I'm going to take, in the numerator, 3 times 2.0001, square that, minus 2, and then I'm going to subtract the quantity of f of 1.999, so that's 3 times 1.999 squared minus 2. All right, so that's the change in my y's, and the change in my x's are 2.0001 minus 1. I use 3 nines. Okay, that's a good approximation. Now, what can we do to get a better approximation so that I kind of have an idea of what my answer is going to be, but I want to make sure. So what can I do to get a better approximation? Yeah, move them closer. Let's add another 9 and add another 0. Are we closer to the value we thought we were going to get? Yeah. So if I add another 9 and another 0, do you think we're going to get closer to the value that we think it is? Yeah. Until, like, man, we're going to be so close, we're going to have 11.9 followed by like an infinite amount of 9s that you can say, well, you're pretty much there. You are approaching, and you will be equal to 12. Fantastic. You guys can find tangent slopes. All right, we're done. And go home now. You don't have to learn anything more. We're good. I'm kidding. Guess what? When mathematicians discovered this in the 1600s, they didn't have calculators. They couldn't do this. Okay? So I'm sorry, guys. We're not going to do this. Okay? They needed to think of another approach to get this value 12. Okay? Because you could try to do this by hand, but do you want to, by hand, take 2.0001 and square it, and then multiply it by 3, and then subtract 2, and then take 1.999 and square that by hand, right? It's not realistic, and it's not the way we're going to do this. We need another approach, okay? Though we want the answer 12, okay? But I need another way to get this 12. So the other approach needs to come from some analysis. You guys are going to do some analysis, and we're going to figure this out together, okay? So we'll start with looking at just some tangent slope values graphically, okay? So I have this function here, f of x, and I want to plot some tangent slope values. Now, when I say tangent slope values, I can, instead of saying that, just write derivatives. But whatever. For right now, we'll be obvious and we'll say tangent slope values. Okay? Now, I'm going to focus on 5 points. -2, -1, 0, 1, and 2. And I would like you guys to do this because I'm doing it as well. Sketch little tangent lines at these points. Okay, go ahead and sketch those on that function. Right, did you get that? All right. Now, knowing that if I have a line that is going up from left to right, my slope is positive. Being greater than 0 means you're positive, okay? If I have a line that's going down from left to right, we know that slope value to be negative. And if we have a flat line, horizontal line, we know that slope is 0, okay? Well, what I'm going to do is, I don't know exactly what the value is, but I know, what the sign is, and I can compare signs. If you have the same value, I can compare values. Is I'm going to say, okay, here at -2, so here at -2, the slope is negative. So I have a negative slope value. I'm going to plot that negative tangent slope value. Okay. If I look at -1, I see this slope is negative. Now, it's less steep than this. So this might be like a slope of -4 or something. This looks like a slope of like -1. So I'm going to plot a less negative value right there. And then I look at 0. Now I'm not looking at 0, I'm just looking at the slope here at 0. I see the slope is 0. Okay, it just happened to be 0. So that means that x equals 0, I have a slope of 0. And then if I look at 1, I have a positive slope. And then at 2, I have a more positive slope. So I have a positive and then a more positive. Okay, this is interesting. You look at this, you immediately say, hey, they're like on a line. Well, I mean, are we sure they're going to create this like nice looking line? Let me just double check. Let me go in the halves. And I can see, okay, that's -2, that's negative. That's going to be positive, but less positive. That'll be more positive, but less positive. So yeah, they fit in between all of these dots. So it looks like I can connect these because I could continue to plot more and more slopes and all of my points would end up being on this line. Okay? Now, this is very interesting. I have a graph of an equation that can tell me tangent slope values to another equation. Like if I look anywhere here, 1.5, I see some positive value. Well, if I look at this graph and I look at 1.5, I see, oh yeah, there's that positive value. Okay? It seems like there is some equation. Take a break in the middle of this. There's an equation, there is some function that will show me all the tangent slope values to this function. And we are going to call this guy f prime. F prime, what is that? That's just like a tick mark. and we call it f prime. It's not a different function. We don't want to call it like a g of x or like an h of x or like something like that, because this is a special function. This is something that is telling me tangent slope values to something else. Okay, cool. Well, I don't know, do all functions end up with a line of tangent slope values? Let's find out. Let's look at a different function. This guy is an f. I would like you to graph f prime values starting at -2, -1, 0, 1, and 2. And let's see, do these tangent slope values end up being placed on a line? Why don't you plot at least the values for these 5 points, 1, 2, 3, 4, 5, and then check with a neighbor, make sure their 5 points are where your 5 points are, and we'll see what type of shape we create. We start, if you're not sure where to start, by sketching tangent slopes. Now the tricky one is here at 0. Okay? At 0 we see there's a positive slope. Then we plot the values of those tangent slopes. So if the slope is negative, plot something below the x-axis. If the slope is 0, plot it on the y=0 x-axis. Okay, go ahead, check with your neighbors. Do you get the same thing that they do? So this slope right here, that's 0. So y=0 would be where you'd plot that point. So it's really that point at 0 that tripped you up there. See, we have a positive slope, which is different from here, where we have a 0 slope. So, negative slope, 0 slope, positive slope. Oh, are we on a line? Nope, because we have another 0 slope, and then I have another negative slope. So all of a sudden, nope, these f prime graphs, not necessarily a line in this case, and if I looked in between and started plotting more and more tangent slope values, we would see that we would create some sort of parabola or U shape, maybe a V shape if you're, depending on the function, but in this case, it's a U. All right, well, this is different than being a line. What this is telling us is that each function, each f of x, has a unique graph of its tangent slopes. It's not going to be consistent. We're not always going to have lines. We're going to have unique equations. Okay, there's some equation that can give me the graph of this. There's some equation that can give me the graph of that. Okay, and that's important. So these f prime tangent slope value graphs, they are unique to its f. Okay. Now, if we think about this, and this is how we have to start thinking about our alternate approach to get that the slope of the tangent to 3x squared minus 2 at x equals 2 is 12. Our alternate approach might be, knowing that I have some sort of kind of friendly function that can show all of the tangent slope values to the original function, if I could find this equation, whatever the equation may be, I could just plug 2 into it, and I would get 12. I would plug 2 into it, whatever this equation might be, it's some mx plus b equation, and I'd get 12. Okay? Now, how would we find that? We'll get there. But let's practice continuing to sketch these unique f prime graphs for this guy and the next guy, just to show you that each of these f prime tangent slope graphs is going to be different depending on the type of function that you start with. Sometimes they're interesting looking. Start by sketching tangent slopes on the graph of f. Then understand the tangent slope values. Plot those on the graph of f prime. Maybe do a little bit extra work to make sure that you are consistent, and then go ahead and sketch. Fantastic. So we see all of these slopes are negative, and they're all consistent. So I should be plotting a negative value, and the same 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 negative value. And I get an f prime graph of tangent slopes that is a horizontal line. Now let's think about tangent slopes. What do they tell me? They tell me how quickly a function is changing. Does it make sense that the graph for f produces a horizontal line f prime? Please discuss that with your neighbors if that makes sense.
Yeah, it's not changing. Like the rate of change because
We are perfectly correct. We are consistently moving down at the same rate. So my tangent slopes or my rate of change is consistent. Okay, cool. Well, let's look at something completely different, something with like an asymptote. Here, this is f. Let's look at its f prime. Okay, now we're going to do this together because it's actually kind of important to not just pick -2, -1. Go ahead and pick a half and like a fourth and like an eighth. Like sketch some extra tangent slopes. An eighth, a fourth, a half, 1, and 2. Okay? Sketch some just random tangent lines on this function. Just start with that, and then I'll kind of show you how we would plot them. But that's where we start. We always start with sketching the tangent slopes. I got that guy there, I got that guy there, that guy, that guy, that guy, this guy, that guy, that guy, that guy, that guy. Now tell me, what is a value if my slope is straight up and down? Undefined, right? So this slope is undefined. What's another way you can write something that's undefined? Like 1/0. Okay? Now, let's pretend it's not exactly 1/0, but it's 1/0 from the left or 0 from the right. What is that approaching? Infinity. So if you think about an undefined tangent slope, it's actually like a slope that is getting greater and greater and greater, either in the positive direction or the negative direction. So like right here where I'm talking about almost having a vertical tangent slope, we're talking about having just an extremely negative tangent slope trending towards negative infinity. So let's start plotting these. We've got negative close to 0, negative, more negative, very, very negative. So negative, a little bit more negative, more negative, a lot more negative. So it looks like we got this. Oh, this is cool. Looks like it's the exact same thing as F. Now I got asymptote at 0. So I got an asymptote at 0. So I'm not going to put anything there. But let's go just to the right of the 0. Am I going to put a very, very large positive value like the graph of F? No? What do you think, Mr. Jones? What is the slope? Yes, it's going to be very, very large and negative. And then we're going to get less and less negative. This is still negative, 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 negative. So actually this tangent slope graph is very, very similar to the original graph, but a little bit different. All right, without screaming out the answer and giving all of your neighbors plenty of time to get their answer to this multiple choice question, if this is f of x, what would be its tangent slope friend f prime? Its unique tangent slope graph. And then make sure everybody's got an idea on this one before we move on. Check again. Check again. If we need to check again, start with how you did the other ones. Plot some tangent slopes. Understand signs of those slopes. Okay? All right. Well done, everyone. Answer is B. Okay? Positive, less positive, 0. Negative, but not very negative, 0. Positive, more positive. Positive, less positive, 0. Negative, not super negative, 0. Positive, more positive. Boom. Okay. Well, this is great. Now we know that there is some equation. You know, this is some like x squared equation. I don't know what it is, but I know that there is an equation out there for this f prime graph. And if I can find the equation, I can plug in any single value, find the value for the f prime, and that'll tell me, oh, the slope of f at this point is this y value. It's something positive. Well, boom, over here, we're something positive. The slope is something positive. Okay? How are we going to do that? Well, this is what mathematicians took a while to figure out. You know, this was kind of discovered in the 1600s. Most of the big math stuff was figured out with like Pythagoras and the Greeks, you know, way back in the BCs and the very early ADs. Okay? This took a while. How are we going to figure this out? Well, what we need to kind of formulate is like some sort of formula that can work with any function at any location. And so we know the existence of these f prime functions. They have equations, but I need to be able to find those equations. What are we going to do? Well, let's try to develop a formula that can be used for any equation for any x value. Okay, so I'm going to try to focus on just this f of x, which could be any f of x. I'm just using a picture. And I'm going to focus on this location x. I want to create a tangent line at x. Okay, this is any function at any value. Now, that means that point right there is f of x. And we're going to find the slope between 2 points starting at x on a function. And remember, slope, and this is just slope, this is nothing crazy. To find a tangent slope, we'll start with a slope formula, something that we've used many times throughout our mathematical lives. Okay? And I will start with a secant line. So I will take 2 points. I'm not going to call this just like a random y. I'm going to actually say it's related to my first point at x. I'm going to say it's an h distance away. So if I add an h distance, this would be x plus h, which means this guy up here is f of x plus h. Okay, and this is just the slope between these 2 points. All right, well, I'm going to take x and f of x and replace it with a and f of a. And I'm going to take x plus h and f of x plus h and replace the b's. Why don't you guys go ahead and do that? And we will have just a slope formula of 2 points h distance away. We'll call this a secant slope. H distance away from each other. All right. Immediately you notice something. Discuss with your neighbors the first thing that you notice. So we notice the x's go away. Okay, so here's my slope of this secant line of 2 points h distance away. And this should make sense, right? It's a change in y over the change in x's. Well, what's the change in x's? It's just this distance, h. So, of course, the x's will go away. So I have f of x plus h minus f of x over h. Okay, fantastic. Well, I wanted not a secant line, I want a tangent line. So I don't want that line there, I want this line here. But I'm going to have to use, a line connecting these 2 points. But I can change something about this situation with the 2 points so that I can develop a tangent line at x. What can we do with this situation with these 2 points? Manipulate it so that all of a sudden you're like, oh, yeah, that looks like a tangent. Discuss that with your neighbors. Mr. Gunwell, what do you think?
Of what you did?
No, what do you think we should do to get a tangent line? I'm calling on you because I usually overhear people who are saying the right things. So if you usually just repeat your ideas, you're usually correct.
Getting closer, so that line would be closer.
Right. So just like how we're getting better and better approximations, just how we tried to find an exact value of a slope at 2, we used 2.001 and 1.999. Well, we can't use like just to the left to the right. It's really just the same as if I take this point and move this point closer and closer and closer together to x. Now, it can't be right on top of x, because then it's definitely 0 over 0. I can't have something that's definitely 0, 0, but I can approach 0 over 0. Now, what happens to this line segment? Does it get smaller? Sure, yeah, it's very teeny tiny. But if we connect and extend those 2 points, what are we going to create? This tangent line, okay? Now, so we're taking our points and making them very, very close to each other. Anybody else come up with that idea? Nod your head if you did. Okay, good. What changed over here? The distance between them, h. What happened to h? It got smaller and smaller and smaller until it got how small? Infinitely small. So approaching what value? Now, what is the concept we've been using in this class where we're talking about approaching values but never getting there? A limit. Very nice. Very nice, everybody. So, if I want a tangent slope, I need to take the limit as h approaches 0 of these 2 points. And this is just an equation, a slope formula for 2 points infinitely close together for any function at any x value. And you're like, great. What does this mean? Well, this is important. This is like magical. This is a key, conceptual breakthrough that happened in the 1600s. That if we wanted to find the equation for the graphs that we created, we can use this magical formula. It is so magical that we call this the definition of the derivative of a function. This, my friend, is the magical formula that we will use to find the equations of the graphs that we were sketching. Okay? Don't believe me? Let's try it out. Now skip the whole keys to remember and notations. We'll come back to that. Let's go here. Now this is different from what it says in your notes, so please change it to what I have here. This is on the next page. We're going to go back to that first example that we did using a calculator, where we had 3x squared minus 2, and we were looking at 2, and we found the slope of the tangent using our calculator, and what did we find that the slope was probably? 12, okay? So let's just remember that. And we got that using a calculator. It's not very realistic. It's not what you could do in the 1600s, okay? And also, it will take a lot of time if we want to, do a lot of these calculations. What if there's an easier way? Okay. So, I want to find f prime of x. I want to find the equation for the graph that we found. Now, 3x squared minus 2, what does it look like? It looks like this. My goal is to find the equation for this line. What is this equation? Okay, so here we go. We are going to use our magical formula. F prime of x will equal the limit as h approaches 0 of f of x plus h minus f of x all over h. Now you're probably like, great, what do we do with this? Well, we start plugging stuff into the formula. I can plug in 3x squared minus 2 for f. Well, I need to plug something in for x plus h. How do I do that? Well, it's actually not hard at all. If f of x is 3x squared minus 2, then f of x plus h means wherever x is, replace it with x plus h. So that's like, okay, wherever I have x, replace it with x plus h. Use parentheses when we replace. Okay, go ahead and take that and plug it into my formula. Everybody do that. You need space, so don't write big on this situation. Go. Plug it in. Let's use our formula. Okay. Don't forget the h in the denominator. And now we have a specific situation here where we are going to find the f prime, the unique f prime for this function, 3x squared plus 2, x squared minus 2, using 3x squared plus h squared minus 2. Minus, and this is important, and did you do this when you rewrote it? Did you use parentheses around f of x? Because I'm subtracting all of f of x. So make sure you subtract the entire 3x squared minus 2. Over h. And we're finding the limit as h approaches 0. It's a limit question. We've done limits. All first unit we are doing limits. Okay, we have limits that look just like this. Our first attempt would be to plug in 0. Now if I plug in 0, I get 0 over 0. What does that mean you should do? Simplify. Okay, so use some algebra right now. What kind of algebra? Let's square the x plus h. Let's distribute the negative sign. Okay, go ahead and start doing that. You know how to do it. You don't have to look at me doing it. This is not new to you finding a limit like this. Maybe check up after you do it. If for some reason you already know the answer, pretend like you don't. We distribute the 3. Now stuff should pop up. I was like, oh, yep. Those 3x squareds, they cancel. Minus 2 plus 2, that's gone. Leaves me with just 6xh plus 3h squared. What do I do now? Factor an h out. What is the last step? Plug in 0 for h. Don't forget that. So my answer is 6x. What is that? That, my friends, is the equation for that graph that we already created, which we knew exists. It has a simple equation, 6x. Okay, so if we go back to our graphs that we already created, if I go back to right here, what is f prime of x? If this is 3x squared minus 2, what is its unique tangent slope graph? 6x. What can we do with that 6x? What does this mean? Does that mean the slopes of my tangents are 6x? Well, that means I can plug in values into f prime to find the tangent slopes of f. We know that the slope at 2 of 3x squared minus 2 is 12. Can I get 12 from 6x? How did I get it? Plug in 2. We say f prime of 2 would be the tangent slope to f at 2. Plug in 2, I get 12. I already got 12. This is our alternate way to get that same value. Okay? This is using an alternate approach and a conceptual approach rather than a brute computational approach. Now, what's great about this alternate approach is if I wanted to focus on another point, like x equals -1, right? What is the derivative of 3x squared minus 2 when x equals -1? I think it's a different number from what you have, so just change it to x equals -1. Like, yeah, if I had a calculator, I could do f of -1.001 minus f of -0.9999 over, hold on, I'll get there, -1.0001 minus -0.99999. Great. I'll start calculating that. Meanwhile, you guys can tell me like that what the answer is. Okay? Discuss with your neighbors what the answer is. Make sure we're on the same page here. -6. Why? Because we have an equation that gives me the tangent slopes of 3x squared minus 2 anywhere. How did I get -6? I just plugged it in to f prime. Question, Ms. Fowler?
No, I'm good. I'm just figuring it out as I go.
Fantastic. One of those days. Okay. Well, isn't that a lot quicker? If I picked another value, like at 4, would I want to type into my calculator f of 4.00001, 3.9999 divided by 4.001, 3.999? No. And what if like I end up with a decimal value and it's like I don't know what value I'm approaching? No, this alternate way, man, is very, very powerful. It'll become even more powerful once we move into the next unit. Okay, great. Well, not only can we find tangent slope values, but I can actually graphically see that we found the correct slope at the correct location. And I can write equations to tangent lines. Okay, so at the end of last lesson, we were reminding, if we watched the video and got through all the scratches, I reminded you of equations of lines. And we will be using the point slope form of an equation of line frequently. Okay? All we need is a point. The x1, y1 is the point. And m is the slope. All right, well, let's think about this situation here where I have 3x squared minus 2. And let's just focus right first at 2. Okay? Here's that line. And I want the equation of that line. What was the slope of that line? We found it 2 different ways. That one was 12, right? At 2. 1, 2. All right, how do we find that it was 12? Well, I used my calculator, but then I found the friendly function, 6 prime, the tangent slope generating function, f prime, which is 6x. I plugged in 2, and I got 12. So the slope in this case was 12. Where did that come from? F prime of 2. Which is 6 times 2. Where do we get a point from? Discuss that with your neighbors. Mr. Belvedere, what do you think?
You just plug in the like x equals 2 to the original equation.
Yes, the tangent line is essentially passing through one point, the point of interest, the point at x equals 2. Where is that point? That point is a point on the function. Shh. I know you're not getting it, but just don't distract anybody else or me. And try to focus. Thanks. This is going on YouTube, by the way. Fantastic. So, the point is a point on the function. So, it's going to be on f of x, which is 3x squared minus 2. I need to plug in 2 into f of x. And I get 10. So where is this point? Where is this line passing through? Passing through the point 2, 10. So I get an equation. Y minus 10 equals my slope of 12, which came from f prime, a tangent slope generating function, gives me the tangent slopes to the original function anywhere, times x minus x1, which is 2. You guys develop the equation for the tangent line to 3x squared minus 2 at x equals negative 1. Check your equation with a neighbor. Not 12. Think about here at negative 1. When we're over here, the slope we see is negative. To find the exact value, we use our friend f prime of x equals 6x, which is the equation of all of the tangent slope values for f. If I want to know what this actual value is, I plug in negative 1, because that's where our x-coordinate is. My slope is 6, giving me my other equation, y minus 1 equals negative 6 times x plus 1. Okay? Now, what's great, to confirm that these are correct, we can graph them and visually see. Now, fortunately, in this class, you don't have to solve for y ever. Unless we need a simplified y equals form on like a multiple choice question. If you were asked on a quiz, on a free response question, hey, give me an equation of a line. These, my friends, are equations of lines. Are they in y equals mx plus b form? No, but I don't care. They're an infinite amount of solutions, xy solutions, that when plotted will be a line passing through 2, 10 with a slope of 12. So this is an equation of a line. This is an equation of a line. We're done. You don't have to solve for y, so please don't put it in y equals mx plus b unless you really have to. Got me? Save yourself some time and some effort. Now an easy way to graph this without solving for y equals mx plus b is just to add 10 and to add 1. 3x squared minus 2, negative 6, x plus 1 plus 1. 12, x minus 2 plus 10. Watch. Here is my 3x squared minus 2. Here's my negative 6x slope, and there's that tangent line. And here's my slope of 12 and that tangent line. Okay? It's a beautiful thing. We just created that. Okay? How do we do it? Well, not by using our calculator to find a slope using 2 points very close, but by finding this f prime function, this equation of tangent slope values. Okay? And we're going to do it with a different type of function. Now let's just like kind of quickly look at what f looks like, maybe in the top corner, and then kind of sketch what f prime is going to look like. Okay, so the square root of x plus 1, that ends up starting at negative 1, 0. It doesn't go to the left, it will go to the right. And it's going to look something like this. Okay? Now, that means our tangent slope values are going to start close to, negative 1. What is the tangent slope value like right to the right of negative 1 on that square root function? Sketch it. Throw a couple tangent slopes down on that guy. This all makes sense if we start from the beginning. I see we have a very, very positive tangent slope value and then getting less and less positive, right? So it's almost like I'm up here and then I'm kind of floating down here. Not a great job by me. Okay? All right, so great. That's what it looks like. But now let's find the actual equation for this graph. Okay, because we can use this equation to tell us the exact tangent slope values of root x plus 1 anywhere. Here are some key things to remember, because we're writing an equation. So go back to key things to remember. Starting with f, we use this formula. To find f prime. Okay? Now, once we have f prime, we plug in x's into f prime, and we'll get tangent slopes to f. Now, if we want points on a tangent line, we'll plug in x's into f to get points on our function, which will be locations that tangent lines pass through. Okay? Key things to remember. Okay, so remembering those key things, let's go back to this example. Our goal is to find an equation of a tangent line, not just the slope of the tangent line, the actual equation. We'll start by finding the equation for this f prime graph. Okay, everybody, plug in the correct things for f of x plus h and for f of x. Write small. We're gonna need space here. Okay, replace f of x plus h and f of x for this specific situation. F of x is easy. We need to replace f of x plus h. Wherever we have x, replace it with x plus h. Okay, if I plug in 0 for h, I'm going to get 0 over 0. Indication that I need to simplify. Guess what simplification technique that we have used back in Unit 1 that we need to use now? Not reciprocal. Exactly, the conjugate. Now, remember the conjugate is just the entire left side and then an opposite symbol and then the entire right side. Hey, if we didn't do great on the Unit 1 test, guess what? The stuff doesn't disappear on us. Not yet. Make sure you multiply the top and the bottom. This is not new. We have done things just like this before. Okay, make sure we understand we have a squared minus b squared. So square root squared, square root goes away. Minus the square root squared, the square root goes away. Careful, we are subtracting all of b squared. Make sure you put that b squared in parentheses. In the denominator, we'll have h, don't distribute it, times the conjugate. Man, roots are tough, honestly. Okay? We can go from there. This negative sign can be distributed. We see that the x's cancel and the 1's cancel, leaving me with just the h. We have multiplication, simplification's friend. We have 1 over. Now, we got rid of that h in the denominator, which is really the key. It will now enable me to plug in 0 for h. Once I do that, I get 1 over root x plus 1 plus root x plus 1. Adding two of the same things together, I can write it as 1 over 2 root x plus 1. And that, my friends, is f prime of x. Watch, just for fun, we know what this is going to look like. We already graphed it just by looking at tangent slope values. You probably have never graphed 1 over 2 root x plus 1, but you actually know exactly what it looks like. It's got to look like this graph right here, right? Let's see, 1 over 2 root x plus 1. Graph. There you go. Now, it doesn't show that you're going as far up as you should be going because we're like approaching an asymptote, but right there. Pretty cool. Okay. I made sure you got there. You take it the rest of the way. Find the equation of the line tangent to the graph of f of x equals root x plus 1 when x equals 8. So give me the equation of this line. Oh, that's horrible. That line. That's not good either. I might give up. I'm going to give up. There you go, that line. There you go. Pays off. Check your answers with a neighbor. If you have a graphing calculator, do yourself a favor and graph square root of x plus 1 and graph the line that you just developed and see, is it correct? Here you go, Sal. Knock yourself out. You got one? Fowler, you check yours. You good, Mr. Seegi? You want one? Look out. All right. You got a calculator on you, Ms. Shambo? Graph them. See the beauty of what you just discovered, okay? It's very satisfying, trust me. You write down an equation, and that's like great and all, but if you graph it, I know what happened. You got to add 3 to both sides, right?
Okay.
Yes! Isn't that great? Gosh, beautiful. So rewarding. Plug in x's into the function to get points on my function. That is going to be the point where my tangent is passing through. Plug in x's into your f prime to find the exact slope value. And then graph for the reward. Okay? Just for my friends on YouTube, we can graph as well. Y equals root x plus 1, and y equals 1/6 x minus 8. Don't distribute, just add 3. Isn't that great? I wish I could like zoom I mean, I can change my window just to see it a little bit better. Let's focus on -2 to 20. Yes. Okay. All right. And how do we get that? I mean, you didn't have to graph it. You didn't need to use your calculator at all. Okay. You found it by finding this guy. Man, that guy is fascinating. That guy is powerful. That guy came from, you know, a slope formula. This is just a slope formula. It's the slope between 2 points at any x for any function infinitely close together. It's all slopes. We're just finding slopes using slope formulas. All right, well, one more. You guys get it started. Then pause, because like this is a common denominator one that's a little tricky. Okay, so at least get it started. Okay, pause here if we're not sure what to do. Now, what students do incorrectly is they're like, oh man, I just need to add an h. That's x plus h plus 3. And they're like, I can add an h, right? Doesn't that work? That doesn't work. Think about it. Use numbers. If I have 1/2, and I add 3 to the top and the bottom, and I get 4/5. Is 4/5 the same as 1/2? No. Okay? So, no. No. Okay? We can multiply by 1. You can't just add by something that if you divide turns out to be 1. So I actually have to multiply by the entire other denominator to get a common denominator. It seems like tedious and annoying, and it's like, do we really have to do that? Yeah, we actually have to do that. I'm going to go ahead and distribute the 2 into the x plus 3. I'm going to make sure I'm subtracting the entire 2x plus 2h plus 6. I have a common denominator, so I can subtract those. And don't forget that dividing by h is like multiplying by 1/h. So you need a 1/h over there, or you could slide this h into that denominator of the first fraction. Okay? Then we can distribute that negative to both the 2x, the 2h, and the 6. And I realize that my 2x's cancel and my 6's cancel, leaving me with negative 2h over x plus 3, x plus h plus 3 times h. Well, the h's can now cancel. Last step is to find this limit by plugging in 0 for h. Now, I could distribute the x plus 3, so it's x squared plus 6x plus 9, but it's a little nicer, a little easier to work with if I just have x plus 3 squared. So it doesn't matter. Either way, it'll work. Okay, we got that. Fantastic. Now, write the equation of the tangent line and, graph it for the rewarding experience. You got -2 over x plus 3 squared. You're looking at 1. You got -1/8 as your slope. You plug in 1 and you get a half. So make sure you're looking at just that guy. This guy is tangent to that guy. And, my friend, make sure when we solve for y, we add a half to both sides. Did you graph? Was it fun? Isn't it fun? Math is fun. Calculus is fun. Now, sometimes we get caught up in creating these equations of these lines, but what was our goal here? Our goal is to figure out how quickly is this function 2 over x plus equals -1. Boom! -1/8. What does that mean? That the function is going down at a pretty slow rate. Okay? That's the instantaneous rate of change. We can say it's decreasing 1/8 of a y for every x at that moment. Okay? When you graph the function y equals 2 over x plus 3, and you look when x is, zoom, standard, you look when x is -1, you can see, yeah, my function is going down, but you can tell that it's going down slower and slower and slower as we move over to the right. Okay? Well, how slowly is it moving down? We found out it's moving down at this rate, -1/8 of a y for every x. It's nice to be able to see that tangent. Oh, I don't know what I pressed. It's nice to be able to see that tangent. What is it, +1? 1/2? Yep, +1/2. Okay, fantastic. All right, so what did we do? We started thinking about slopes, and slopes at a specific point. Well, use 2 points very, very close together. You can use your calculator, use the slope formula, great, but not realistic, okay? Very, very computationally intense, can take us a long time, even when we're plugging it into a calculator. So we needed an alternate approach. So our alternate approach started by first understanding that there are these f-prime functions, these graphs of equations that give us tangent slope values to original equations anywhere. Okay, and they're unique to the original equation. So a parabola makes a line. And then we have some sort of x cubed, and it makes a parabola. We have some sort of y equals mx plus b, and it makes a straight line. We looked at something like a 1 over x, and it looks like negative 1 over x squared, if you're familiar with that. Okay? And it's like, well, how do I find the equation of that? We developed a formula for an equation for the slope of a tangent, which is just using the slope formula for 2 points infinitely close together. This developed a magical formula. We are now able to plug functions into that formula to find the equation of those graphs that we first discovered. Using that equation, we now can tell the tangent slope or the instantaneous rate of change to the original function anywhere. Okay? Yeah, that's exciting. Oh man, I feel like I skipped some stuff. Anyways, last thing. Are there situations where we cannot differentiate? What does differentiate mean anyways? Just means like we don't have a tangent slope. Like a derivative is a tangent slope. It's an instantaneous rate of change. If you say differentiate, it means like find a tangent slope. So are there situations where we cannot find a tangent slope? Discuss with your neighbors what you think might be some situations where tangent slopes don't exist. What do you think, Ms. Belmares? Do you have any ideas for locations where we probably maybe don't have a tangent slope? Yes. Actually, all discontinuities, including holes. If we have a jump, it's like, where do I draw a tangent line? You know, do I draw it here? Do I draw it there? So, no tangent slopes at jumps. At asymptotes, where we don't even have a point. How can I draw a tangent slope if I don't even have a point? And actually, since I don't have a location for the tangent to go through, I don't have a tangent line that occurs at a hole. Okay? We have to be continuous to have a tangent slope. But that's not it, because there is situations on continuous functions where you don't have a tangent slope. So, can anybody brainstorm a situation with a continuous function where at one location we don't have a tangent slope? Discuss. The piecewise function says jumps, so they would not be continuous functions. But a certain type of piecewise function where they connect, yeah, that can be continuous, and yeah, I can see where there's a point where there's no tangent slope. What type of situation am I talking about? Any ideas? Oh, very interesting, Ms. Belmares. An absolute value graph. What does an absolute value graph look like? Like a V, right? Some piecewise functions, when they connect, they make, you know, sharp points, like boom, and then yoink, like that, something like that. Well, let's think about drawing a tangent slope value, or more than that. Let's think about how is a function changing right here at the sharp point. Is the function going down or going up? I'm not sure. If I look at kind of like the slopes to the left and the slopes to the right, they're looking at different values. It's almost like I want to draw a horizontal line, but it's not going to be mimicking the function because the function has a sharp value. It's not like flattening out like our other zeros, okay? So it's actually at this location, very, very good guess and assumption there, that at a sharp point, there's no tangent slope. We call this a sharp point or a cusp. Right here, sharp point. We can't draw a tangent slope there. At a sharp point, there's no tangent slope. Another situation, depending on kind of the book and who you talk to, if you have a vertical tangent slope like this, some people will say that we don't have a tangent slope because the tangent slope is undefined. Slope there, so I think it's fine. But if you're going through some book problems and you're like, why are they including that? Oh, it's because it's a vertical tangent, and vertical tangents have undefined slopes. Does that make sense? All right. Good job.